Okay, ladies and gentlemen, so in this unit, we're going to be talking about motion and forces. And just like in the last unit, right, we're going to take a few notes and then we're going to have our project at the end. So this one is going to be our balloon car projects. So these cars are basically built by just random stuff that you probably have lying around your house, mostly recycling stuff or trash, and it's powered by balloons. So if you look at like the slideshow right now, you'll see that some of these cars, what they're kind of made out of, they're all powered by a balloon. So ultimately, when we're done taking notes for the next 4 weeks, you're going to have to build it using the knowledge and the concepts that we've learned throughout the class over the next 4 weeks. So that's our main goal when we, as we continue to work on this project or this unit. But let's start with our notes. So first slide is our vocabulary. All right, so there's a few vocabulary words that we need to go over for this, just for this week. So the first one is the reference point. And a reference point is basically to compare something that's moving. Right? In order for us to know if something is moving, you have to compare it to something that seems like it's not moving. So for example, let's say a car goes by right in front of you. How do you know that it's the car that is actually moving? Well, it's because you're probably looking maybe at the building behind it, and you see that the building is not moving, but you see the car moving in front of it. So that's how you know, and that's what we call is the reference point. All right, it's the object that's not moving. All right, and then likewise with motion. All right, now remember, I'm always going to be highlighting as I'm doing this, so you should make sure that you have a highlighter as you work on your notes. All right. Motion and reference point go hand in hand because when you're talking about the reference point, you have to be talking about an object that's moving. All right? You know an object is in motion because you're comparing it to a reference point. So that object that's not moving. And if that object looks like it's moving, it's probably changing its position compared to that. All right? And then position. Position is very similar to the word distance. We're going to probably use this interchangeably. All right, and basically what the position means is how far is it from the reference point. Okay, so when a car goes in front of, starts moving, from the building, how far is it from the building every single time I measure. All right, last one is the speed. All right, this is a big part because a lot of the stuff that we're going to be doing in this unit is all about speed. Right? And speed is just like you use this word all the time, is how fast an object is moving. All right? And in science terms, we talk about how the rate at which an object changes its position. So how fast is it moving from one spot to the next spot? That's what speed is all about. Okay, so we'll be doing a lot of speed calculations throughout this unit. Right? And so as I keep going through this set of notes, remember that I'm probably going to go faster through each slide than what you can write. So make sure to pause it as we keep going along. Right? So let's talk about just a hypothetical idea of what it really means to be in motion. So right now you're sitting in your chair, right? And you think that you're not moving. You're not in motion. You look at the ground, your feet aren't moving, your body's not moving compared to the ground. So if the reference point was the ground, absolutely, you're not moving. But some people would say that you are moving, and you're moving at hundreds of miles per hour right now, right? And you're sitting there going, what? How am I moving at 100 miles per hour? I don't feel it, okay? Well, that depends on its reference point. Let's say that my reference point, and I'm going to put RP because I don't feel like writing it all out. Let's say that the reference point was the sun. Okay? So we look up at the sun, right? And we see that every day the sun is moving. Well, guess what? If I were standing on the sun, what would I see the earth doing? I would actually see the earth moving, right, in a circle. And it would also be rotating. So in that case, everything that's on the earth is moving. So therefore, if the earth is moving, then you're moving. And the earth is moving at hundreds of miles per hour. Okay? So when we talk about something that's moving or in motion, it's really important that we understand the reference point. What are we comparing it 2. All right, so right now, yes, if you compare it to the floor, you're not moving. But if you're comparing it to the sun, you're absolutely moving. Okay, so when we talk about things that are moving, you got to make sure that you understand what you're comparing it to, which is the reference point.
Okay, so we can express motion using these three variables. And using these three variables, we can also quantify motion through equations. I call them the speed equations. So basically, the three variables are speed, right, distance, and time. And those all tell the story about the motion of any object that we have. So using these three equations, we can figure out how fast an object is moving. We can talk about how far an object has moved. And then we can also talk about how long it took for that object to move in that time span. So the way these three equations work is the first one, this is probably the one that you're going to use the most. It's speed equals distance divided by time. Now the way I'm going to usually write it out, because I don't want to write out all these words all the time, you're going to see it written as S equals D divided by T. Okay? That's the first equation. The second equation is distance equals speed times time. So I can express distance, right, by just doing speed times time. So you'll see it written as this one, right? This is the first equation. Oops, sorry. It's the first equation. Why is this not working? There we go. All right, this is the second equation, right? And the third equation is time equals distance divided by speed. Okay, yes, these are three equations you will have to memorize for this unit, right? But these are the three speed equations that can tell us what's happening to the motion of an object. Okay, so now let's talk about how do we use these three equations in word problems. All right, so first one is this. There's 3 steps to every problem that we do. And yes, I expect that every single time that you do a speed problem or motion problem, you're going to be using these 3 steps. Okay, so step 1, right, is you always write down what you know. So since I have 3 variables, I'm going to always write down S equals, D equals, and T equals. What this is going to help me do is it's going to tell me what am I solving for. So that way I can go back here and I can figure out what equation I need to use. Do I use this one, or this one? Okay, so on the first one, I read, Amy walks north for 5 minutes and travels 200 meters. How fast did she walk? So clearly when I read the words, how fast did she walk, I know I'm solving for speed. So I'm going to put a question mark next to speed, right? And then I know that distance is 200 meters because she travels 200 meters. And again, remember, I'm always writing my units. And it says that I'm traveling 5 minutes, right? So now that I know that I have these 3 things and I'm solving for S, my next step, my second step, is to figure out which of the 3 equations that are listed here do I use. So since S equals my question mark, I'm going to use the very first equation. Right? Whatever I'm solving for is the one I'm going to use. So I'm going to use this one. S equals D divided by T. Right? Now my third step is what I call the plug and chug. Right? So now I'm just going to plug these numbers in to this equation. So S equals 200 meters over 5 minutes. Right? And if I put that in my calculator, I'm going to find out that S equals 40 meters per minute. And there you go. And I just solve for speed. Okay, and I put a box around it. All right, let's try another one. All right, it says Tony rolls down a hill at 6 meters per second and travels 54 meters for how many seconds? Right, so I'm looking at for how many seconds, right? So that tells me time. So when I do my first step, I'm going to write S equals, D equals, and T equals. So since I'm asking for how many seconds, I'm going to put a question mark next to my time. Right? And I can see that I'm moving at 6 meters per second, and it's a distance of 54 meters. So now, when I go to my second one, I know that T equals my question mark, right? So I'm going to use T equals. So if you forget, right, if I go back to here, I'm going to use now the third equation because it says T equals distance divided by speed. Right? So I'm going to come back here and I'm going to type this in, write this in. Right? Now I know. So now my third step is just to plug and chug. right? So I'm going to put t equals, my distance is 54 meters, and I'm traveling at 6 meters per second. So if I solve that, put in my calculator, I know that that is 9 seconds. And there's my answer. Okay, so this is how I use those three equations to solve word problems.
One was, how do you find the speed using in a word problem? So now we're going to use it in a graph. So just like before, right? And I can't say this enough. That's the reason why I keep constantly highlighting this. Speed equals distance divided by time. So again, right? I'm going to write speed equals distance divided by time. Right? So in this case, let's say that I'm using a graph and I want to find the speed, the average speed of this entire graph. Right? So what I'm going to do is I look at this graph and I see, okay, I see time and I see distance. Right? Position. Remember, position means the same thing as distance in this unit. All right. So again, a graph is the same as a word problem. The only thing is you're just not reading anything. For some of you guys, this is really, really simple because you're sitting there going, well, I don't have to read anything. That's awesome. So just like last time, I'm always going to do the setup exactly the same. I'm always going to go S equals, D equals, and T equals. Right? So in this case, I'm trying to find the average speed. So I'm going to put a question mark next to the S. Right? And the next thing I'm going to do is I'm going to find the distance and my time. So if I read my graph appropriately, what I'm going to do is to find the average speed, I'm always going to use the last point. So I'm going to circle it for you. All right, that's the last point. So from here, I can find the distance and the time very, very quickly. So right here, because I know that my label right here, this is distance, I just draw an arrow over to my distance. And that's 40. So I know that's 40 meters. All right, now I'm going to move to my time. If I look time, take that last point and go all the way down, it's 20 seconds. So that's how I find my distance and my time without using any words. So there's no word problems. But the graph tells me all this information. Right? From here, right, I just use this equation. S equals D over T. And I can calculate it. So let me go back to black. S equals, right, 40 meters divided by 20 seconds, which equals 2 meters per second. And that is my answer. Okay, so if you look at it, the work is exactly the same as what I did with the word problem. The only difference is I'm using my graph right here to find the distance and the time. All right, so again, some of you guys might find this to be really, really simple. Some of you guys might find this to be a little more difficult than using a word problem. All right, but the work is the same. All right, so let's say that this time I want to only find not just the speed of just the whole graph, but let's say I just want to find the speed of one little section. So if you look at it, it says calculate the speed from 5 to 10 seconds. So let's say I told you I only want to find the speed from here to here, just these two, between just these 2 points, and that's it. All right. So now I got to use, instead, I got to find the slope. So when I find the slope of a distance versus time graph, I'm actually finding the speed of an object. So in your math class, you should have learned that slope equals rise divided by run. All right. So if I look back over here, it's the same thing. I'm going to do the same exact work that I've done throughout the entire note so far. I'm still going to go S equals, still going to go D equals, I'm still going to go T equals. Okay, now, but in order to find the D and the T this time, it's a little bit extra work. All right, so the first thing is, right, I'm looking over here, here's my distance, just like last time. All right, so what I need to do is I need to first find my rise, because that's what's going up and down. All right, so if I want to find from one point to the next, I'm going to draw 2 arrows. One that goes here, and the other one that goes here. And you'll notice that it goes from 20 to 30. How much did it go up? it went up 10 meters. Okay, oh, and I need to put a question mark here. So the next thing is my time, right? So I look down here. So let's put this in blue so that we can see it's time. And this is my run. This part's my run. So what I'm going to do is I'm going to draw 2 more arrows going down to this point, from that point to this point. And what I'm going to look for is how far did it go over? Well, it went from 5 seconds to 10 seconds. So that equals, right, 5 seconds. So that's step. So then the next step I do is, just like last time, I'm going to write down my equation that I need to use. S equals D divided by T. Right? So then I get, and then I just plug in the numbers. S equals 10 divided by 5. And if you're wondering how I got that, so remember my distance equals 10. My time equals 5 seconds. So now S equals 2 meters per second. And there you go. Okay, so that's another way that we can find the speed of an object. And this one's a little bit more precise because you're now asking yourself to do it from one point to the next point. All right. All right, so the last one. How do you find the speed of an object using just a data table? Okay, so in this case, let's say I say calculate the speed from 0 to 60 seconds. And again, I'm using this equation. And obviously I have this highlighted over and over and over again because I want you to understand how to do this. Okay, so let's say I've got now a data table. So far we've learned how to calculate the speed using a word problem. We've calculated speed using a graph. Now you're going to have to know how to calculate speed using just a data table. So here again, the main things I want you to look at is time and distance as my labels. So again, if I show the work, same thing as I've done the previous 3 times. I'm going to go S equals question mark because that's what we're looking for, speed. Right? And then we need to now look for distance. So this one it says from 0 to 60 seconds. What do I use? That means that I am going to use, again, the last point, the last set of data in order to do that because it's going all the way to 60 seconds. So what is my distance at 60 seconds? 60 meters. Oh, and this should probably, actually this should say 0 to 6 seconds. I don't know. I made a mistake. Sorry about that. Okay? And then the t, right, at 6 seconds should be 6 seconds. Right? So now if I use the equation, so again, I'm going to write it out. S equals 60 over 6. Right? So I plug it in, distance divided by time. So S equals 10 meters per second. And there you go. All right, so that's how you find it. So again, if you look at all of your notes now, so if I go back, look at the work I've shown here. Look at the work I've shown here. Look at the work I've shown here. And look at this work I've shown in here. I know it's crazy looking, but if you look at it, the work is exactly the same. The only difference is how do you get the information is just a little bit different. Okay, but whether it's through a graph, data table, word problem, it's all the same way to do the problem. Okay, you use this equation, speed equals distance divided by time. All right, we're almost done. Okay, so last keywords that we need to talk about is the difference between velocity and speed. Okay, we use these words a lot. You probably use them and you probably think they're basically the same thing, and they are, right? There's one big difference between speed and velocity. Speed is just how fast it's going. I'm going 60 miles per hour. I'm going 20 miles per hour, right? That's speed. Velocity actually has to have a specific direction, meaning it's speed, but you're going somewhere. So you have to say, I'm going 60 miles per hour east. I'm going 20 miles per hour north. right? You're telling somebody which direction that you're moving. So if you look at these examples right here, right? Look at the difference between this one, oops, this one right here and this one. All right, this one, they're written the same. The only difference is velocity right here has east. And that's it. That's the only difference between velocity and speed, right? Is which direction is it going, right? And again, if it changes directions, then the object changes its velocity, but the speed stays the same, right? And I need to hurry and finish these notes because my daughter's starting to wake up. So if you start hearing a crying noise, then you know that I'm trying to speed up real quick to finish up because I can hear her. But anyway, so hypothetical question again, okay? So Dale Jr. So if you ever watch NASCAR, right, they always talk about these people's speeds and they talk about velocity of their car, right? So let's say that Dale Earnhardt Jr. is a NASCAR driver. He's driving his car, and he's driving around an oval-shaped racetrack, and he's going at 189 miles per hour. So his speed is 189. The question I have for you is this, right? This one right here. So how is it that even though his speed is staying the same, 189 miles per hour the whole time, that his velocity is changing though? So his speed stays the same. So he's staying 189 miles per hour the whole time around this track, but his velocity changes. Like, how is that possible? Okay, well, if you think about it, let's look at an oval track, right? This is the track that he's driving around. And so usually on a track, they're driving so that they're always taking left turns. All right, so he's driving this way at one point, then he'll turn and he's driving this way, and then he'll drive this way, and he'll drive this way. Okay, well, the velocity changes because his direction constantly keeps changing. This one, he's going up, and then he's going left, and then he's going down, and then he's going right. So even though he's going 189 miles per hour the whole time, because his direction, right? So his direction changes. Oops. That means that his velocity is changing. So that's another big difference. So that's how you use kind of velocity and speed at the same time, is that way. So a lot of people actually use it incorrectly. So like sometimes like the NASCAR, like the people who are doing the commentating, they'll say his velocity. Well, really, they're not using it right. They should be saying their speed the whole time.